Hi Math 98. This is our last video for our last lesson, 4.3. It's going to be a little bit shorter maybe than some of the other ones. So I just want to go through it. Hopefully you had a chance to do the P&L already. You saw in the P&L that it was talking about Social Security retirement age. So meaning that depending on when you were born, you have to work until a certain age before you can collect full Social Security retirement. So in this lesson, what we're looking at is kind of how that retirement age would affect different populations, different demographics, if it were raised to 75. So if you read the paragraph on the first page there under the problems situation, it talks about how there are always going to be people, unfortunately, who pay into Social Security because of a job, but then pass away before they're able to collect that Social Security. So the trouble is if they raise the Social Security age too high, then more and more people actually will never be able to collect their Social Security retirement. So that's a concern. So that's what we're looking at here in this lesson. So the graph on page 456, number 1 there, I just did a rough kind of sketch of it up here. It's not exact, and I don't have all the grid lines in, but it's the same general idea. Okay. So what we're talking about here is African American male life expectancy at birth. Okay, as I said, we always want to orient ourselves to the graph. I didn't write the title up there, but you have it in front of you. This is life expectancy at birth, and this is years since 1900. So here's what this means. This is the year we're looking at, birth year, okay? And so this number is just the years since 1900, kind of like we did with the milk consumption, right? So 20 here means 1920. 100 years since 1900 is 2000. Okay, this is 2020. You notice there's actually no value for 2020 because it wasn't 2020 yet when this was made. So it goes up to 2010 is the last point there. Life expectancy at birth. So what this means is that for African American males, if they were born in 1920, their life expectancy, they're expected to live 46, 47 years, okay, wherever about that is. If they were born in 2000, their life expectancy is about 70 years. So that's what that means. Overall, through time, life expectancy has gone up in general because of advances in healthcare, medicines, vaccines, just general cleanliness sort of, right? We have running water, we have sewers, things like that. We know more about food safety. So just overall, for all population, life expectancy has gone up. Now, you see with any real data, it's not always going to go up exactly the same rate every year. There are little dips here, okay? This is around 1970. I don't know for sure, but I would guess something, maybe the Vietnam War. These are babies that were born then. But, as things happen, there's some kind of, medical concern, a pandemic. There's some kind of a war, there's some kind of a natural disaster. So things kind of shift for those populations, right? So we can kind of think about what those kind of things might be that might affect life expectancy for a certain age, for a certain birth year. So what we're going to be doing is we're going to be creating a linear model, an equation, and a line to estimate this, okay? Now, again, real life data is not perfect like our little latte where it took off $2.63 every time we bought a latte, right? So imagine, though, that we can have a trend like this, or if you took a whole bunch of kids that were from age 1 to age 4 and graphed their age versus their height. In general, it's going to be going up. I mean, there are going to be some really tall 2-year-olds and some shorter 4-year-olds, right? But in general, that's going to go up. So same idea here. We see a general trend. So what we're going to do is get what we call the line of best fit. So it's the linear equation or the line that kind of goes through here, the best estimate, okay? It's not going to touch every line. We're not doing connect the dots. We're finding a line that kind of goes right sort of through the middle. Roughly, we kind of want to have balance on both sides. We don't want to put our line here because then that line is larger or higher, has higher values than all of our points. We don't want to put our line down here. We want to put it right through the middle. So yeah, there's some things that are a little higher, some are a little lower. It kind of balances out. It gives us an estimate of what's happening there. So what I would like you to do, if you have a ruler handy, that would be great. If you don't have a ruler and you have just another sheet of paper, that works too. Or just kind of do your best to draw it in there. Draw a line on that graph on page 456. Kind of straight through those if you can, okay? And you want to bring it back to intersect the y-axis. Okay, so go ahead and do that on your paper. I'm just going to try to do it up here. Okay, another thing that kind of works well if you need to kind of lay something down and see where the line is, a piece of dry spaghetti is nice because then you can see all the way around it. You can see where it goes. So mine's not perfectly straight, but roughly it's going to look something like this. Okay. So we were given just a graph and we want to find the equation of that best fit line. So there are a couple things we need to do. So number one, we needed to draw our line. We did that. So secondly, we need to find our starting value, or we could call this our y-intercept, or in the book they call it the vertical intercept. Okay, I don't really love in this example that in there they're calling this variable y, because this is the y-axis. It gets a little confusing. But we want to find the starting value, which is here. Okay, your starting value is always your y-intercept. Remember, this was for the cell phone plan. It was how much you pay if you use 0 gigs of data. For the lattes, it was how much you had on your card if you had bought 0 lattes. For here, the 0 is how many years since 1900. So this is actually going to be for a baby born in 1900, what was the life expectancy, right? That's the beginning of this data that we're looking at. So we want to find the starting value. Okay, so if we think back to when we wrote equations in 4.1 and 4.2, they're going to look something like this. Here's our life expectancy, or our y value, equals, and we're going to have our starting point, or our starting value, plus how much it changes every year. So we call that the rate of change, or every whatever interval, in this case it's year, times the number of years. Okay. Think back to the milk consumption. Remember how we had to figure out what the milk consumption was in 1985? So we said, okay, here's what it was in 1950. Here's how much it changed every year, and it's changed that much for 35 years. That's how we figured out the new milk consumption, right? The amount of money on your card for your latte was how much we started out with. The rate of change there was negative. So we were saying minus the 263 times however many lattes. So it's the same setup for linear models, or for linear equations. So we found the starting value. My starting value, now, or we can see it right here. Your starting value might not be exactly the same as mine, and that's okay. All right. Our lines are not going to be exactly the same. You might have one that kind of goes up a little and, across this way a little shallower, and that's perfectly fine. So you can use what yours looks like here. You can use mine. It doesn't matter. Mine looks like it's maybe around, 41, right? So my starting value would be about 41. Now I need to find my rate of change. Think about what's another word for rate of change. Well, rate of change is the same as slope. Okay. How do I find slope from a graph? We did this with the milk. We actually didn't find it from a graph. We found it from the information. But remember, we need 2 points. So I want to find 2 points on here. Now, I'm trying to find the equation of this blue line. Okay. So I don't want to use a point that's not on the line. Like, these points are part of my data, but they're not on my line, so that's not going to give me my equation. So I want to either find a point, like a data point, that I really kind of went right through and use that, or, especially on yours because you have the grids, you can choose any point on this line. I could choose this point on this line if I could figure out an estimate of what its values are. Okay, so either of those works. You can also use your y-intercept as one of your points. So I'm going to use that. I'm going to use 0, what did I say? It was about 41. So 0, 41 is going to be one of my points. And I'm going to use, I kind of go pretty much right through this point right here, which looks like it's about 63. I kind of went underneath it. So I'm going to say maybe 80, 62 would be an estimate of roughly what my point is. Okay, so I want points on the blue line, not the dark points that are above or below it. So if I have those 2 points, so I didn't use this one, but I used like this one right here, okay? Those 2 points, remember slope. Slope is, or rate of change, either one, y2 minus y1, x2 minus x1. I subtract the y's, and I subtract the x's. So I'm going to choose to go in this order both times just because it gives me 2 positives. If I went in this order, that's fine. It would give me 2 negatives. Negative divided by negative is a positive, same idea. So 62 minus 41, 80 minus 0. So 62 minus 41 is 21 over 80. So if we divide that, 21 over 80 is 0.2625. Okay, you can call it 0.26, you can call it 0.263. So I'm just going to call it 0.26. Now, rate of change or slope, I want some units on there. Okay, I want to know it's this 0.26, this per this. So think about your units on here. Your y values, this was the life expectancy, and this was the year of birth. Well, this is really the year since 1900, right? But it essentially leads us to the year of birth. So this is my y. So 0.26 years of life expectancy for every year after 1900. Okay, so if our life expectancy in 1900 was 41, let's say, if we simplify this to say, let's assume the rate is constant all the time. We know it's not, but this gives us at least an estimate of what's happening. Then 1 year later, if babies were born in 1901, they would be expected to live another quarter of a year, another 3 months. So every 4 years, roughly, the babies would be expected to live another year. Okay? So this is what we need to do if we're given a graph, what we need to do to find that rate of change. Now, number 2 says, in what year will African American male babies have a life expectancy of 75 years? So I have now my linear model. This is my linear model. And this brings us back to what we did with our blood alcohol content, right? We have 2 pieces of information, life expectancy, number of years since 1900 that the baby was born. So we just are going to plug in for one, solve the other, right? So in this case, we want to know when life expectancy is 75. So I want to know 75 equals 41 plus 0.26y. I'm going to solve for y. I'm going to subtract 41 from both sides. I'm going to get 34 equals 0.26y. I will divide by 0.26, and I will get y equals 130.77. Okay, what does that mean? 130 years after 1900. That means it would be babies that were born in 2030, roughly. I'd have to go out to 130 here to go up to where it was at 75. Now, if you used your own line and your own points, your rate of change may be slightly different, your starting value may be slightly different, this will be slightly different, but it should be roughly the same. And then the final question asks, in what year will these babies be eligible to begin drawing Social Security? When would they be 75? Well, if they're born here, then we add 75 to it. That's the year they'd be eligible for Social Security. Okay, so I'm just about out of time, but we're done with this. There are 3 more graphs for different demographics, and I want you to try them on your own, and I'm going to upload the answers to Blackboard, okay? But this is the end of the video going through them together. All right, thanks guys.